1,000 horsepower. From 1.6 liters, that's not a typo. We're talking about an engine smaller than what's in your mom's Corolla, producing more power than a Bugatti Veyron. And it does this while screaming along at 15,000 RPM for 2 hours straight in temperatures that would melt your dashboard. I mean, come on, this defies everything we think we know about engines. You're probably thinking I've lost my mind. 1,000 horses from an engine you could literally carry under one arm? But here's the kicker. These Formula One power units aren't just producing this insane power, they're doing it while achieving over 50% thermal efficiency. For context, your car's engine is doing well if it hits 35%. Most of the fuel you pump into your tank? Yeah, you're just making expensive heat. The 2014 regulations changed everything. Gone were the glorious, naturally aspirated V8s that sounded like angry Norse gods. In came these tiny, turbocharged V6 hybrid units that sound like, well, let's not talk about how they sound, but what they lack in oral pleasure, they make up for in sheer technological insanity. These aren't just engines anymore, they're power units, energy recovery systems, rolling physics experiments that would make Einstein's head spin. Here's where things get interesting. To understand how these pocket rockets make their power, we need to dive into what is essentially black magic, masquerading as engineering. And trust me, by the end of this, you'll either want to become an F1 engineer or check yourself into therapy. Maybe both. Let's start with the basics. The internal combustion engine part, the bit that actually burns fuel, is just 1.6 liters, 6 cylinders arranged in a 90-degree V configuration. Sounds almost quaint, doesn't it? Like something from a hot hatch. But that's where the similarities to anything remotely normal end. These engines rev to 15,000 RPM. Let that sink in. Your car probably redlines at what, 6,000? Maybe 7 if you're fancy. These F1 units are spinning 2.5 times faster. At 15,000 RPM, each piston is moving up and down 250 times per second. The valves are opening and closing 125 times per second. The forces involved are absolutely mind-blowing. At maximum RPM, the conrods are experiencing forces of over 6 tons. That's like hanging an elephant from each connecting rod 250 times per second. The pistons are accelerating at over 8,000 G. For comparison, fighter pilots black out at 9 G. These pistons are experiencing almost 1,000 times that force, every single stroke. The materials needed to survive this are exotic to say the least. We're talking about aluminum-beryllium alloys for the pistons, titanium aluminide for the valves. Materials so specialized that they're basically unobtainium for us mere mortals. Each piston costs more than your entire engine. Hell, each valve probably costs more than your car payment. But materials alone don't make power. You need air, fuel, and spark. And this is where the turbocharger comes in. Now, turbos aren't new. They've been around since the early 1900s. But the turbo on an F1 car is something else entirely. It spins at up to 125,000 RPM. Yes, you heard that right. 125,000. At that speed, the tip of the compressor wheel is moving at nearly Mach 2, twice the speed of sound. The bearing technology required to support something spinning that fast is insane. We're talking about bearing surfaces polished to a mirror finish with tolerances measured in microns. The whole assembly is balanced so precisely that adding a fingerprint would throw it off. This turbo can generate over 5 bar of boost pressure. That's about 73 psi for you Americans. Your tuned Subaru making 500 horsepower? It's probably running 20 psi. Maybe 25 if you're brave. These F1 engines are running 3 times that pressure. The intake air is compressed so much it heats up to over 200 degrees Celsius. That's 400 degrees Fahrenheit. Hot enough to bake cookies. Which brings us to the intercooler, or rather, the air-to-air charge cooler as they call it in F1. This thing has to cool that superheated air back down to something reasonable. We're talking about removing hundreds of kilowatts of heat energy. The intercooler on an F1 car is a piece of art. Microscopic passages designed using computational fluid dynamics that would make NASA jealous. But here's where it gets really clever. The turbocharger isn't just there to make boost, it's connected to something called the MGU-H, Motor Generator Unit, Heat. This is an electric motor/generator connected directly to the turbo shaft. When the driver lifts off the throttle, instead of the turbo slowing down, the MGU-H keeps it spinning, harvesting that energy and storing it in the battery. Think about that for a second. Turbo lag, the bane of turbocharged engines, since forever, completely eliminated. The turbo is always spinning at optimal speed because there's an electric motor controlling it. It's genius, pure genius. When you need boost, it's there instantly. No waiting, no lag, just instant, brutal acceleration. Speaking of the hybrid system, this is where things get properly space age. The MGUK, Motor Generator Unit, kinetic, is connected to the crankshaft. It can add 160 horsepower instantly. But more importantly, it can harvest energy during braking. Every time the driver hits the brakes, the MGUK becomes a generator, turning the car's kinetic energy back into electricity. The battery, or energy store as they call it, weighs between 20 and 25 kilos. About 50 pounds. It can store 4 megajoules of energy. That might not sound like much, but it's enough to power your house for about an hour. And this battery is charging and discharging constantly throughout a race. We're talking about current flows of over 1,000 amps. The cooling system for the battery alone is more complex than most entire road cars. The control systems managing all this are running at frequencies that boggle the mind. The engine management computer is making calculations and adjustments 1,000 times per second. It's monitoring hundreds of sensors, adjusting ignition timing, fuel injection, boost pressure, energy deployment, energy recovery, all in real time. The software running these power units has millions of lines of code, literally millions. Now let's talk about the combustion process itself. This is where the real magic happens. These engines are running compression ratios of over 14:1 with 5 bar of boost. The cylinder pressures are exceeding 300 bar, that's 4,350 psi. The forces trying to blow the head off the engine are astronomical. To contain these pressures, the engine block is carved from a solid billet of aluminum, not cast, carved, using 5-axis CNC machines that cost more than your house. The cylinder head bolts are made from exotic materials like Inconel. Each bolt is ultrasonically tested for flaws. A single crack invisible to the human eye would result in catastrophic failure. The fuel injection system is equally insane. Direct injection at pressures up to 500 bar. The injectors fire multiple times per combustion cycle, precisely controlling the fuel-air mixture for maximum efficiency. The fuel itself is a carefully guarded secret. Each team works with their fuel supplier to create bespoke blends optimized for their specific engine. But here's the thing that really bakes my noodle. These engines are limited to a fuel flow rate of 100 kilograms per hour. That's about 33 gallons per hour for those keeping track. Your average NASCAR V8 uses about 100 gallons per hour. So these F1 engines are making twice the power with a third of the fuel. The efficiency is absolutely staggering. This is achieved through something called lean burn combustion. The engines run with excess air, way more than theoretically needed to burn the fuel. This improves efficiency, but makes the combustion process incredibly unstable. It's like trying to run a campfire with wet wood. The fact that they can make it work reliably is a testament to the engineering involved. The ignition system has to be incredibly powerful to ignite these lean mixtures. We're talking about plasma ignition systems that create a kernel of plasma in the combustion chamber. The spark energy is 10 times what you'd find in a road car. The ignition coils could literally kill you if you touch them. Pre-chamber ignition is another trick these engines use. A small chamber above the main combustion chamber with its own injector creates a super-rich mixture that's easy to ignite. This then shoots jets of flame into the main chamber, igniting the lean mixture. It's like having multiple spark plugs, but way more effective. The valve train is a work of art. Pneumatic valve springs using compressed nitrogen. Metal springs simply can't handle the accelerations involved at 15,000 RPM. The valves would float, bounce, and eventually meet the piston with catastrophic results. The pneumatic system operates at over 20 bar of pressure and has to be perfectly sealed. A leak would mean instant engine failure. The camshafts are gun drilled to reduce weight. Every single gram matters when you're spinning at these speeds. The cam profiles are so aggressive that the valves open and close in a fraction of the time of a road car engine. The valve overlap periods are precisely calculated to use exhaust gas scavenging to help fill the cylinders. Interestingly, these engines don't use variable valve timing. You might think that's primitive, but it's actually because the regulations don't allow it. F1 engines have to make do with fixed valve timing, which means the cam profiles have to be perfectly optimized for the entire rev range. It's like asking a sprinter to also be a marathon runner. The cooling system is another engineering marvel. These engines generate over a megawatt of waste heat. That's enough to heat about 50 homes. The radiators use fluid dynamics that would make aerospace engineers jealous. Every single cooling fin is optimized for maximum heat transfer with minimum drag. The coolant isn't water, it's a special blend of glycol with additives that prevent cavitation. At these engine speeds, the water pump is moving coolant so fast that it can create vapor bubbles. When these bubbles collapse, they create tiny implosions that can erode the cylinder walls. The coolant chemistry prevents this. Oil is equally critical. These engines use dry sump lubrication with oil pressures exceeding 10 bar. The oil isn't just for lubrication, it's a critical cooling medium. The underside of the pistons are cooled by jets of oil spraying at over 100 miles per hour. The oil temperature is controlled to within a degree Celsius. The oil itself is synthetic, obviously, but it's not just any synthetic. It's specially formulated with additives that can handle the extreme pressures and temperatures. The oil film between the bearings and the crankshaft is thinner than a human hair, yet it has to support loads of several tons. One microscopic particle of debris and it's game over. Now here's something that'll blow your mind. These engines are designed to last only about 5,000 kilometers. That's 3,000 miles. Your Camry engine will do that in a month of commuting. But here's the kicker. During those 3,000 miles, these F1 engines will do more revolutions than your road car engine will do in its entire lifetime. Think about that. At an average of, say, 12,000 RPM during a race, that's 20 million revolutions in a single race weekend. Your car at 3,000 RPM average over 200,000 miles? That's about 300 million revolutions total. The F1 engine does nearly that many in its short lifetime, but at 5 times the engine speed and with 10 times the cylinder pressure. The manufacturing tolerances are beyond comprehension. Bearing clearances measured in hundredths of a millimeter. Piston to bore clearances so tight that the engine has to be preheated before it can even turn over. Everything is measured, recorded, analyzed. Each engine has thousands of hours of development behind it. The dyno testing alone is incredible. These engines are run on dynos that can simulate entire race weekends. Every gear change, every corner, every straight. The dynos can apply loads dynamically, making the engine think it's in the car. They measure power to 1/10 of a horsepower, torque to 100th of a newton meter. But making power is only half the battle. Delivering it is equally challenging. The throttle response has to be instant. When a driver climbing out of a slow corner cracks the throttle, they need power now, not in half a second. The engine mapping is so sophisticated that it can predict what the driver wants before they even finish the input. This is where artificial intelligence comes in. Yeah, these engines are using AI, Machine learning algorithms analyze thousands of parameters in real time, optimizing the engine performance for each specific situation. Corner exit, maximum torque. Long straight, maximum efficiency. Qualifying lap, everything turned up to 11. The sound, or lack thereof, is actually by design. The turbocharger acts as a muffler, absorbing much of the exhaust energy that would normally create noise. The exhaust system is tuned for performance, not sound. Every bend, every change in diameter is calculated to optimize exhaust gas flow. Sound is just wasted energy. The MGU-H harvesting exhaust energy means even less sound energy escapes. It's brilliant from an efficiency standpoint, but tragic from an emotional one. The V10 era engines screamed at 20,000 RPM because all that energy was being wasted as sound. These modern engines convert that energy into speed. Let's talk numbers for a second. Peak power is around 1,000 horsepower at about 11,000 RPM. But the power band is surprisingly wide. These engines make over 700 horsepower from 9,000 RPM all the way to the 15,000 RPM limit. That's a 6,000 RPM power band with massive power throughout. Torque is equally impressive. Despite the tiny displacement, these engines make about 350 Newton-meters of torque. That's 260 pound-feet for the imperially inclined from 1.6 liters. Your 2-liter turbo road car probably makes less torque, and it's got 25% more displacement. The specific output is where things get truly ridiculous. 625 horsepower per liter. Your high-performance road car might make 100 horsepower per liter if it's really good. The best naturally aspirated road cars barely crack 130. These F1 engines are making 6 times that. The brake mean effective pressure, basically how hard the engine is working, exceeds 50 bar. Most road car engines are at about 10 bar. High-performance road cars might hit 20 bar. These F1 engines are at 50 bar for 2 hours straight. It's like comparing a marathon runner to someone sprinting up Mount Everest. The fuel efficiency is perhaps the most impressive stat. At full power, these engines are achieving over 50% thermal efficiency. The best road car diesel engines barely hit 45%. The Mercedes F1 engine has reportedly exceeded 52% in dyno testing. That's better than massive ship engines the size of buildings. How do they achieve this? Partially through something called the Molly jet ignition system. Instead of one big flame front propagating through the cylinder, you get multiple jets of flame shooting throughout the combustion chamber. The burn is faster, more complete, and more efficient. It's absolutely brilliant. The exhaust gas temperatures exceed 900 degrees Celsius. That's 1,650 degrees Fahrenheit. Hot enough to melt aluminum. The exhaust manifold glows cherry red during a race. The turbine housing has to be made from Inconel or similar exotic alloys just to survive. But here's what really gets me. All of this insane technology, all of these mind-bending numbers, and these engines are actually getting more powerful every year. The development never stops. Mercedes reportedly had their engine exceeding 1,050 horsepower on the dyno. Honda claimed similar numbers before they left the sport. The development budget for these engines is astronomical. Mercedes was reportedly spending over $400 million per year on their F1 engine program. That's more than $1 million per day, every single day, just on engine development. The dyno facilities alone cost tens of millions. Each team goes through dozens of engines per year at a cost of several $1 million per engine. That's just the hardware cost, not including development. When you see an F1 engine blow up in a cloud of smoke, you're watching several $1 million go up in flames. Literally. The human element is equally impressive. The engineers working on these engines are the absolute best in the world. We're talking about people with multiple PhDs, decades of experience, and an obsessive attention to detail that borders on the pathological. One missed calculation, one tiny error, and an engine worth more than your house becomes scrap metal. The logistics are insane too. Each engine is hand-assembled in clean rooms cleaner than operating theaters. Every single component is tracked, measured, and documented. The assembly process takes days, with multiple quality checks at every stage. One speck of dust in the wrong place and it's catastrophic failure at 15,000 RPM. Transportation is equally critical. These engines travel in specially designed cases with shock absorbers and climate control. They're treated better than most famous paintings. The cases have GPS tracking, temperature monitoring, and even accelerometers to detect if they've been dropped or mishandled. During a race weekend, the engines are constantly monitored. Hundreds of sensors feeding data back to the garage and to the factory. Engineers thousands of miles away are watching every parameter in real time. Oil temperature spike of 2 degrees? They know about it instantly. Slight drop in fuel pressure? Already investigating. The rebuild process between races is meticulous. The engine comes apart completely. Every component is inspected using techniques like X-ray crystallography and electron microscopy, looking for microscopic cracks, wear patterns, any sign of impending failure. It's forensic engineering at its finest. What really blows my mind is that all of this technology will eventually trickle down to road cars. The Mercedes-AMG 1 hypercar uses a modified version of their F1 engine. Detuned, obviously, because no road car owner wants to rebuild their engine every 3,000 miles. But still, a genuine F1 engine in a road car. The hybrid technology is already making its way into road cars. Energy recovery under braking, electric turbocharger assistance, it's all coming. In 10 years, your family sedan might have technology that was winning F1 races today. That's the beauty of F1. It's the ultimate testing ground for automotive technology. But let's address the elephant in the room. These engines don't sound good. They sound like angry vacuum cleaners compared to the old V10s and V12s. And you know what? The engineers know it. They've actually tried to make them sound better. They've experimented with exhaust designs, wastegate configurations, even speakers to amplify the sound. The problem is fundamental. Efficient engines don't make much noise. Noise is wasted energy. Every decibel coming out of the exhaust is energy that could have been used to go faster. It's a trade-off, and in F1, speed always wins over sound. Always. There's something philosophically interesting about this. We've reached a point where making an engine too good actually makes it less exciting. The perfect engine, from an engineering standpoint, would be silent, invisible, and boring. It's like we're engineering the soul out of our machines in pursuit of perfection. But then again, isn't there something beautiful about the pursuit of absolute efficiency? These engineers are pushing the boundaries of what's physically possible. They're extracting every last joule of energy from every molecule of fuel. It's pure engineering poetry, even if it doesn't sound like it. The future of these engines is uncertain. There's talk of increasing the electrical component, maybe going to fully synthetic fuels, possibly even hydrogen. Whatever happens, you can bet the engineers will figure out how to make insane power from whatever regulations they're given. It's what they do. For now, though, we have these incredible 1.6-liter monsters. Engines that, by all rights, shouldn't exist. They're too small, too powerful, too efficient. They break all the rules we thought we knew about internal combustion. They're basically showing us that everything we thought was impossible is actually just difficult. What gets me is the sheer audacity of it all. Someone sat down and said, let's make 1,000 horsepower from 1.6 liters. And instead of laughing, engineers around the world said, challenge accepted. And then they actually did it. They took physics, bent it over their knee, and made it submit to their will. These engines represent the absolute pinnacle of internal combustion technology. We're unlikely to see anything more advanced in our lifetimes. Electric motors might be the future, but they'll never have the complexity, the challenge, the sheer bloody-minded engineering brilliance of these F1 power units. Every time I watch an F1 race now, I can't help but think about what's happening inside those engines. Pistons accelerating at 8,000 G, turbos spinning at twice the speed of sound, temperatures that would melt conventional engines, pressures that would blow normal engines apart, all controlled by computers making thousands of decisions per second. It's absolutely insane, and that's what makes it beautiful. In a world of sensible engineering, of safety margins and reliability requirements, F1 engines are a glorious middle finger to conventional wisdom. They're what happens when you give brilliant engineers unlimited budgets and tell them to go crazy. The fact that these engines even exist gives me hope for humanity. If we can make 1,000 horsepower from 1.6 liters, what else can we do? Cure cancer, colonize Mars, finally make a printer that actually works when you need it to? Okay, maybe that last one is asking too much. Sometimes I lie awake at night thinking about these engines, about the engineer who first proposed pneumatic valve springs, about the person who figured out how to eliminate turbo lag with the MGU-H, about the countless hours of development, testing, failure, and eventual success. There's something deeply human about it all, this relentless pursuit of going faster, of being better, of pushing boundaries. We don't need 1,000 horsepower engines. Nobody's commute requires that kind of power. But we build them anyway, because we can, because the challenge exists, because somewhere deep in our DNA is the need to go fast. And that's really what it comes down to. These engines aren't just about transportation. They're about human ambition crystallized into metal and carbon fiber. They're about taking the laws of physics and bending them to our will. They're about showing that with enough intelligence, determination, and money, we can do the impossible. So the next time someone tells you that a 1.6-liter engine making 1,000 horsepower is impossible, just smile. Because somewhere in Brixworth or Sakura or Maranello, there's an engineer who's already done it. And they're probably working on making it even more powerful. That's the beauty of F1. It's not about what's sensible or practical. It's about what's possible when you remove all constraints except the laws of physics. And even those are more like suggestions when you've got a big enough budget and smart enough engineers. These modern F1 power units are the most complex engines ever created. They're triumphs of engineering, examples of human ingenuity at its finest. They're also completely unnecessary, wildly expensive, and environmentally questionable. But that's what makes them perfect. They're everything that's wonderful and ridiculous about human nature distilled into 1.6 liters of controlled explosions. And honestly, I wouldn't have it any other way. Because in a world that's increasingly sensible, increasingly electric, increasingly autonomous, these engines are a reminder that humans still do things just because we can. We still push boundaries just to see what's on the other side. We still chase that extra tenth of a second, that extra horsepower, that extra percentage point of efficiency. Maybe that's the real achievement here, not the 1,000 horsepower or the 50% efficiency or the 15,000 RPM. Maybe the real achievement is that we haven't given up on being extraordinary. We haven't settled for good enough. We're still pushing, still innovating, still refusing to accept that we've reached the limit. And as long as there are engineers willing to ask, what if we tried this? And racing series crazy enough to let them, we'll keep seeing impossible things become reality. Today it's 1,000 horsepower from 1.6 liters. Tomorrow, who knows? Maybe 2,000 horsepower, maybe 70% efficiency, maybe engines that run on unicorn tears and produce nothing but rainbows and horsepower. Okay, probably not that last one. But with F1 engineers, you never really know. They've already done the impossible. What's a little more impossibility between friends? The only thing I know for certain is that somewhere, right now, an engineer is looking at these current engines and thinking, I bet we can make that better. And that, more than any specification or technology, is what makes these engines truly special. They represent human refusal to accept limits. They're monuments to our obsession with going faster. They're proof that given enough time, money, and clever people, We can violate everything except the laws of thermodynamics. And we're probably working on those too. So here's to the F1 engine. 1.6 liters of insanity. 1,000 horsepower of pure distilled human ambition, the most remarkable, ridiculous, brilliant piece of engineering ever created. Long may it scream. Well, whir. Long may it whir at 15,000 RPM.